Hi everyone, welcome to IoT Deep Dive. Today we are going to walk through a full end-to-end solution connecting a device. This device is going to be the ESP8266 up to the cloud and visualize data. So I am joined here today with Wellington and Ewerton. Super excited. These guys are going to lead this deep dive. I'm going to play host and mod in the live chat. So if this is your first time joining into a deep dive, these are live events. So I'll be answering all of your questions when it comes to Azure IoT, our SDKs, and how to start visualizing data. And then Wellington and Ewerton is actually going to go through that full experience for you. So Wellington, did you want to give a little bit of information on what you do on the team?
Absolutely. Yeah, thank you, Pamela. I'm Wellington Duraes. I am the PM for the C SDK and Embedded C SDK. And yes, it's a pleasure to be here today.
Yes, I'm excited. We get to geek out a lot about hardware, so it's great to have you on this video. And then Ewerton, do you want to talk about what you do on the team as well?
Hi everyone, my name is Ewerton, and I've been a software engineer of the CSDK team for almost 6 years, and now engineer on the Embedded C SDK team now.
Wonderful. Well, thank you so much, both of you. I'm going to let you go ahead and lead this event, and I'll be in chat. So, and don't worry, if you're viewing on demand, you can definitely reach out to us on Tech Community, and we'll talk about that at the end. So go ahead and Wellington, and take it over.
Thank you, Pamela. And so everyone, as we're saying, we're going to share the story about the Internet of Hazelnut. It's a story about how tiny and inexpensive devices can make a difference to small business. This is based in a real life scenario. And to begin with, just in case you're wondering what Hazelnut is, think about Nutella, right? So Nutella is based on hazelnuts, and as any produce, as anything that is cultivated, there's always that issue with the production and demand, meaning that you have a spike once a year when farmers are growing hazelnuts, and then they need to store this somewhere so that they can sell and so they can have this production year-round. So the best way to store grains and so hazelnuts as well will be using one of these silos. So obviously, if you're a big farmer and you have resources, very likely you'll be using these huge silos that have multiple controls for a lot of things. And at the end of the day, as we've learned, maintaining grain quality in silo storage is a science. So there's a lot in terms of the perfect moisture, what is the ideal temperature, how to keep pests out of the silo. So all good information that is at the reach of, again, big farmers. But if, for small farmers, they eventually will be using small silos and maybe not have access to all of this technology. But guess what? Again, using small microcontrollers, we could help farmers like this one to keep their hazelnuts in a good shape all year round. So let's take a look at what this high-level solution for the Internet of Hazelnut would look like. So here we have a picture of the silo. And as you can see here, we would have an IoT device. So this is a connected IoT device. As Pamela said, this is based on the ESP8266. This device is connected to a number of sensors, so say humidity and temperature sensors, sending information to this device, which is then taking this information and sending D2C or device to cloud telemetry messages to the cloud, to hub. And it can also take commands or C2D, cloud to device commands from the cloud. These commands could potentially do things like turning the fan on and off on the silo, but also this device here has to be able to turn this fan on and off according to the humidity that it is taking here. Because every time the humidity gets too high, you need to ventilate internally the silo so we can get fresh air in, so we can remove the humidity. So this will be the high level view of the solution.
Hey, Wellington.
Yeah.
When we're developing solutions for IoT, there are many platforms and technologies that we can use. And like, for example, it's very common to use LoRa, Bluetooth, LE, Sigfox, and cellular, for example.
Yeah.
Why did you choose exactly the ESP8266 with Wi-Fi for this solution?
Oh, great question. Well, I would say that for this sample is mostly for simplicity. First, because the ESP8266 is small and it is cheap, and also because I believe that people watching this video would have Wi-Fi available for their tests. Clearly, in a real life scenario where a farmer would have the silo, I don't think the silo will be at the reach of a Wi-Fi network, right? So in this case, if this was a true real life scenario, we would likely to be using either cellular or narrow band IoT, any of these narrow band IoT scenarios, which use cellular network to be connected. And eventually, even so, this silo could be in a place so remote that not even cellular signals are getting there. And then we'll be looking at something like LoRa to connect them. BLE for Bluetooth Low Energy is really not the case for an application as big as that. But Ewerton, to your point, this with Wi-Fi is just for simplicity. But as we will be seeing, the SDK we'll be using here is modular. So eventually folks watching this video can replace the Wi-Fi stack for LoRa or for cellular easily. Okay, then moving on. So we are getting the ESP8266 as the device, and we're saying that here we have the silo application, and we need a way to make it easy for this device to connect to Azure. And so we'll be looking at one of the Azure SDKs. So when it comes to connecting devices to Azure, we happen to have a number of different SDKs. So SDKs comes in different flavors. So here, as you can see, we have the C SDK, we have the C# and Java SDK. These for potentially for machines with full operating systems like Windows or Linux. We also have Node.js and Python SDKs. All of them have in common the fact that they provide the whole set of features for Azure IoT, like as we're mentioning, D2C, C2D, direct methods, device twin, device provisioning, IoT plug and play. All of them provide that. But the one piece missing in this family of SDKs was an SDK for tiny devices, MCU-based devices or constrained devices. And then it comes the embedded C SDK to this picture. On the embedded C SDK, we have some guidelines when we're creating it. And so this will be the 6 tenets of the embedded C SDK. So first and foremost, optimizing for size. So we kept in mind size at all times. Second, giving the customer choice. And then avoiding dynamic memory allocation. Actually, we don't have any memory allocation on the embedded C SDK. We're fully embracing MQTT as an industry standard. We're creating this concept of bringing your own network stack. And finally, we like to consider this our everywhere SDK, meaning that if you have a device that can connect to a network, it is very likely this device can run the embedded C SDK.
Very interesting, Wellington. It's very interesting to see all the options we have in terms of SDKs. And we had the CSDK from the beginning of Azure IoT, and it has been used on platforms like embedded Linux for a long time. What is the real advantage of having this embedded CSDK for this project?
For this project in specifically, Ewerton, I would say that it is the footprint, right? So as we're saying here, right, optimizing for size, I would say that the footprint using the embedded C SDK compared with, say, the C SDK, in this case, is much smaller, which allows us to use really tiny devices to run the Internet of Hazelnut. That will be basically the point.
Makes sense.
Cool. All right. So, okay, provided that we'll be looking at the embedded C SDK, let's see at how this application will look like. So, as I said, embedded C SDK. And while we could think of all of these Azure IoT features, for this sample, we'll be using only telemetry and commands. So, CDD and DTC messages. We'll have an application code. And as I said before, the embedded C SDK, it provides choice to developers, which means that developers can pick and choose whichever MQTT client they would want. So this could be Paho, Mosquito, or any implementation that is specific to the MCU, the microcontroller that you're using. The same goes for TLS, and the same goes for socket. As you can see here by the color, it will be for the IoT developer to choose whichever stack they would prefer, also creating their code. And then we, Microsoft, will be providing you with the embedded C SDK. But let's move from this theoretical view to take a look at what is the reality that we're creating here. Ewerton, moving to you.
Yes, so the project that you've created is based on the sample that we have on the repo that we've created for the ESP8266 board using Arduino as a development environment. And the creation of the sample is a very good idea of what the customers are going to see when they're developing with the new embedded C SDK. Basically, we knew what was the application that we wanted to do, which was we wanted to use a application on the board to talk to the Azure IoT Hub and do telemetry, for example. Based on that, we knew that the embedded C SDK was capable of doing those features that we needed, and was based basically on MQTT. The embedded C SDK is not an MQTT client. It provides you all the tools you need to feed an MQTT client, the topics, information for the connect, and also helps parsing the responses that you get from the IoT Hub. From there, the solution was created just basically choosing the components we wanted. And the process was just search for an MQTT client that was appropriate for that environment. In that case, we just went ahead and among all the MQTT clients that we had, we just got one that is popular for Arduino itself, which is the PubSub client. Then from there, we wanted a TLS stack that would be as small as possible. And there are different options, Wolf SSL, Embed, TLS. We just went with Bear SSL, which is also very tiny. And finally, we just needed to put this all together in a solution with a socket layer. And the ESP8266 board comes with all this API that you can use from Espressif that provides you the Wi-Fi abstraction that you can use with the solution. So we just put it all together.
Nice. So Ewerton, quick question here for you. So the fact that in this case here, we're using a PubSub client, Bear SSL, ESP8266, this is just one of the possibilities, right? Customers could mix and match whichever TLS and socket they want, correct? Absolutely,
because the embedded C SDK is based, it's only helping with the MQTT primitives based on MQTT 3 spec. Mm-hmm. If you bring any MQTT client that is capable of supporting MQTT v3, it can be used with the C SDK. And the only other requirement you would have here is to bring a TLS stack that is capable of doing TLS 1.2, at least TLS 1.2 to connect with the Azure IoT Hub.
Got it. So TLS 1.2 is a requirement from Azure IoT Hub, right?
Correct.
Got it. Awesome. Yeah, thank you for that.
Absolutely.
Okay, so let's take a look then at what the device looks like. So as we were seeing in the previous slide, we would need, on top of this device, we would need a couple of sensors, and we'll also need to control the motor or the fan that would be ventilating the silo. So let's take a look at what this would look like. If you decide to build, you can use this as the footprint for that. So as you can see here, we're using a standard breadboard. We're using a Node MCU, which is the ESP8266 Wi-Fi chip on it. And then basically here we only have this device. Might be hard to see because it's white. So this is the DHT. In this case, because it's white, is the DHT22, but you can use the DHT11 as well. This is the temperature and humidity sensor. You'll also need a 10 kilo ohm resistor here. Then we have the motor, the fan motor. In this case, because this is a 6 volts motor, all we need to control it is a transistor, so BDX33. And then as you can see here, another 1 kilo ohm resistor. And we also have an LED here just to show when there's a command to turn the motor on. So you'll see this device working in practice in a couple of minutes. And so finally, so this is getting to the demo time. So what we'll be demoing today is the device. So we'll see the ESP8266 working, connected with the sensors and with the motor. We have on the sample that we created, it was created to locally control the airflow in the silo. So it keeps reading the humidity, and every time the humidity goes beyond 60%, it turns the fan on and then off again when it goes below 60. And it keeps sending messages reporting the temperature and humidity to the cloud at every 2 seconds. And this is something that is configurable. And also, this device can get commands from the cloud. So if you decide that you want to turn this on for a test or for anything remotely, you can turn it on. So we can override the 60% rule and turn the fan remotely on and off. Now, clearly, if you have a real-life sample for that or need for that, you can add multiple sensors to a scenario like this. You could use, a silo capacity. So we could have here one of those distance sensors that would measure how much of the silo is in use. So in this case, here will be 50% usage. You could have dust levels, which in silos is a pretty dangerous risk of explosions, presence of different gases like nitrogen or something like that. So multiple sensors for that. Now, we're just going to take a minute to flip from this machine to the demo machine, and we'll be back. Okay, so now we completed the transition, and as you can see on this camera, we have the device as we were sharing before. Now I have the device fully assembled here, as you would have it as well if you wanted to see it working. And so let's take a look at how to connect this device to Azure. Okay, so first step is to look at the Embedded C SDK. So it's just going to aka.ms/embedded-c SDK. Within here at this README page, and here you have the getting started guides and the samples. So if you go here to the samples, you'll see that we have samples for Linux, Windows, and the ESP8266. So let me click on this one here. Okay, and there you go. How to set up and run the Azure SDK for Embedded C IoT Hub client on the expressive ESP8266 Node MCU. Let's take a look at what are the prerequisites. So it's having an Azure account. I do. Azure IoT Hub must be created, and we need to have a logic device, the latest Arduino, And one of the following, so will be Azure command line interface on either Windows or Linux. And also we could have the Azure IoT Explorer, which is the one I'll be using today. Okay, so set up and run instructions. So Ewerton is here and he'll be helping me with this. So first things first, I'm on Windows, so I'll follow this piece here, which is the PowerShell scripts, correct, Ewerton?
Correct. Usually we would have a library directly on the library manager of the Arduino IDE for the Azure SDK for C, but we don't have that yet. And in this case, we're just providing a way to generate the zip library locally.
Okay. Run as an administrator?
Correct.
Is there anything I need to set up here before running this?
No, you can go straight with that. If you were using the PowerShell without administrator permissions, you could just set the execution policy to unrestricted, for example. That would allow you to run the scripts.
Okay, so I moved back to the root. So running this.
Yes.
Okay.
This is pretty much just getting the script online, and then you just need to run it, and it will do the whole work for you.
Oops.
Oh, little syntax there. You just need to do a /.
Okay, it will be before or after?
Before.
Like this?
The other slash.
There you go. Like this?
Yes.
Oops. Okay. Running scripts is disabled on this.
Interesting. Yeah, you can run the set-execution policy. Dash execution policy. Space unrestricted.
And then I go all, yes, to all A.
Yes.
There you go.
Now you can just run the script again.
Cloning. Good. So I should have on the C drive. Oh, there you go. Yay, Arduino SDK library. Okay. Step 1 generated. So run into step 2, run the Arduino IDE. So this is just opening, right?
Correct.
Okay, got it. And then install the Azure SDK library.
Just on step 3, did you have the ESP board already installed?
Oh, no, I don't. So let's look at the instructions here. Okay, so I remember this one. So here I will take this board manager link, go back to Arduino IDE, File, Preferences, and here under Additional Boards Manager, I need to add this link, hit OK, go to Tools, Board Manager, and then here I will type ESP8266. When I see this here, I'll hit, is that a good version?
That is the latest, and that is the one that we use to test the sample on the main repo.
Good. So I'll hit install on this one here. It might take a while according to your internet speed, but luckily this is going well here today. Yay. Okay, while this is installing, let's take a look at what will be the next step. So going here. Yeah, thank you for the call out. So done this. It will be installing the library.
Yes, in this step, we're going to install that zip library that we just created.
Oh, okay, the one we created with the PowerShell script.
Correct.
Got it. Okay, so, okay, the board support is installed. So then I go to Sketch, include library, add zip library.
Correct.
Then I go to the C drive. This one here, right?
Correct.
Okay. Hit open. Okay, library added to your libraries. Okay, so we should be good now.
Yes.
Cool. Next step. PubSub client. Oh, this is the one you're talking about for MQTT, right?
Yes, that is the MQTT client we selected for this sample in particular. No specific reason for using other than it's just a popular MQTT client for Arduino.
Got it. So that is sketch, include library, manage libraries.
Correct.
And here, there you go, it's PubSub.
Client.
Oh,
It's
client.
Yes.
There you go. And then we're looking to, here you go, PubSub client by Nick O'Leary.
Yes.
Install.
Citations are important.
Yes. Okay. Normally, this would be enough to run the sample that you get out of the box. For this particular case, because we're using that DHT11 sensor, we did an additional library. So I need to go here and type DHT11 to get this DHT sensor library by Adafruit. So I will install this one. And it needs additional library, so let's say install all.
And Wellington, just to clarify, as you mentioned, this library is not needed if you're running the sample that is on the main Azure SDK for C repo. This is only needed for the project that you're demoing today.
That's correct. But if folks install this by accident, that's totally fine. It won't take a lot of time or space. So yeah, if they do this by mistake, it's not gonna break anything, right?
Absolutely.
Cool. So we have step 5, which is the PubSub. Then we will create a sketch. So for that, we need to clone the Azure SDK for C. So let me copy this link. I go to git cmd. Oops. Okay, C, make their, oops, if I can type, src, cd, c, and here I go git clone -- recursive and Azure SDK C. Okay, done. Let me close this. And it says that I should open the ESP sample, which is under, as you can see here below, it says SDK sample IoT. So let me take a look at that. See, SRC, Azure SDK, SDK, samples, IoT, AZIoT, right?
Correct.
ESP8266. So this one here.
Yes.
Okay. So let me open this guy now. Okay. So again, right, Ewerton, if all I want is to run a basic sample to test, this code here is enough, right? Is all I need.
It's all you need, and the only thing you need to feed is all the configuration on that other header, the IoT configs, which you're going to be touching soon for your project as well.
Yes, yes. However, folks, for this Internet of Hazelnut sample, we have a slightly different code that is taking advantage of the humidity sensor, and it's also controlling the motor. So let me go ahead and grab that additional file. So for that, I'll go back here, and then I go aka ms. For this one here, it will be IoT-Hazelnut. There you go. That's the grain silo INO. I will click on raw, and then Control A, Control C. I will go back to the sample. So let me close this one. Go back to the sample. And then on this first tab that says AZIoT ESP8266, I will go Control A, delete, and then Control V. So I am pasting the code here that I took from this gist. Okay.
And Wellington, this code is pretty much the sample we have on the main repo, plus everything that you were using to collect the data from your sensors and exercising telemetry in the commands, correct?
Yes, yes, yes. That's
Very
exactly
good.
it. Cool. All right. So I will now need to change. So if we go back here again to see the instructions, it says that now we need to edit IoT configs.age with the Wi-Fi and password. Let me do that. So IoT configs, SSID, wonders2, password. Okay, is it that? Yes, it's a very complex password. All right. And then I need the Azure IoT credentials. So as the instruction said, you need, before doing this, your Azure account, the hub must be created, and you need to have a logical device. And as I said, I'll be using the Azure IoT Explorer. So this is the Azure IoT Explorer, is an app that you can have on your machine, and you can access, let me go back to home here. So you can access your hub, and you can control and create new devices. So if I click on this hub that I created just for this video, you see all of the devices that I have. So here I can create new devices. So in fact, let me create a new one here. And I call this Silo Demo. Authentication here, Ewerton, symmetric key is fine.
Yeah, for simplicity, we're using symmetric key.
Okay, so that's now just he creating, right?
Yes.
Okay, so create, okay. And now if I go back here, it asks me for the device ID. So if I go here, the device ID is Silo Demo. So I can either copy it here, or I can go to this nice button here that copies the content. So I go back here, paste, and then it also asks for the device key. So that will be the primary key. So let me copy, go back here and paste. And finally, it also asks for the IoT Hub fully qualified domain name, FQDN. So that I get by going back to the hub. And it says here, C is the name of my hub. So I can either copy just a small first part, or I can copy the whole content, go here and replace all of these. So I can get a nice hubname.azure-devices.net.
That's perfect.
This should do it, right?
Yes.
Let me go back here just to see what is the next step. Connect ESP to your USB port. Check. On the Arduino, select the board and port. So, okay. So yes, go back here. So tools, board, and then ESP8266. Because you see here, as it shows here, it says Arduino Uno, which is the default when you install Arduino IDE. So we need to change that board. So tools, board, ESP8266, and then find the node MCU 1.0. There you go. And it also says that I need to find the port. So this is connected. So if I right click on the start button, I go to device manager. And then if I expand ports, there you go. I can see in this case here, that's the USB to UART bridge is on COM4. So COM4 is what we're looking for. So I'll go back to the Arduino IDE, tools, port, and I will select COM4. And just because we want to make this upload quick, I will just change the upload speed to 256. There you go.
That was a very good tip you gave me last time. That makes the whole upload to the board so much faster.
I know, it's twice as fast, right? And I tried faster than that. Don't do that, it won't work. So this is as fast as you can go with ESP8266. So upload the sketch. Sketch upload. Okay, so we're ready to see some action here. Nice. So yes, it's uploading. It's writing, as you can see here, almost 100%. Okay, it says now done uploading. So now it's time to open the serial monitor by clicking here. Let's see. All right, Wi-Fi connected, got an IP address. What is this doing now, Ewerton?
The ESP8266 doesn't have hardware to maintain a clock. So, and we need that for connecting properly with the Azure IoT and for generating the SAS token. So we need to connect to an NTP server and get the time during runtime. That's what that is.
Got it. Got it. It misses the RTC, real-time clock.
Yes.
Got it. Okay, seems like it is already sending the payload, which is the device ID. What is the temperature? This is in Celsius. The humidity and light. So let me now check to see if this information, so this is the serial information. So basically, this is what the device is sending back to my computer. So this is all happening locally, but we want to check if this data is actually getting to Azure. So let us open the Azure IoT Explorer. That's the hub I want. And we created this device here called Silo Demo. So now if I open this one here and I click on telemetry and start, we should see data flowing from the device to Azure. Oh, there you go. So we're seeing here the temperature, humidity. Yay, it's working. Now, remember I said that there is that little control. If the humidity goes beyond 60%, it turns the fan on and off. How about we test that so we can also see if the humidity data here will increase, right? So let me hold here. So I'm holding just my finger against the sensor, and we're seeing if when it reaches 60%. Oh, there you go. It turns the fan on. It works. Let's see. Oh, there you go. 64 here, right? 64%. If I keep my finger, it will keep going up. Also, the temperature goes up a little higher too, but it takes a little more time. So let me remove my finger. So we can see the humidity. There you go, going down again. And yes, the fan on the device stopped. Now, the other thing that we implemented is the ability to overwrite this setting. So I can go here to cloud to device message and just send a message that says yes or Y, send. And let's see if the light in the device, there you go. So the device is now on. And likewise, I can send a message N with the no and send a message again. And there you go. The device goes off.
Very nice. Wellington, just one question about your project. That is pretty cool to see it working. The first part where there's the temperature sensor and it activates the fan, that logic is local, correct? It's sending the temperature and information to the cloud, but the device in the local application is checking the humidity and activating the fan directly. Now, on the second part, you were doing, you're using the direct methods from Azure IoT to manually.
Actually, it's cloud to device.
Cloud to device, exactly.
Cloud to device.
Sorry. Yes, yeah.
No,
cloud to device message to activate that. All right.
Yeah. Yes. So that's it. Now you're seeing that once this data is on the hub, is on the cloud, then you can create whatever application you want. So you can have alerts, so you can have logic, you can store this data on a SQL database, so you can have multiple other options and possibilities for your application there. And actually, we did something along of those lines. And provided that this data is already in the cloud, we created this time series insight, which is a time series database. And we have, as you can see here, 3 devices connected and getting the information of, here we have temperature for 3 devices, and we have the humidity. And one of the things that if I am a farmer and I have these 3 silos filled with my produce, I will be very interested to know that, okay, how's the humidity going on? So we know that the silo will have the fan to keep it to keep the air flowing, so it won't get too damp, too humid. But look at this one here. So you see that this silo, which is in my case here, I'm naming outdoor silo, there was this spike in the humidity that goes all the way up to 94, and it was there for a long time. So if I'm a farmer and I see one of my silos like that, I would immediately think one of the 2 things could have happened. So first, either the fan that is supposed to keep the air flowing is broken, is not working, and because of that, the humidity is going up, or maybe there's a leaking, there's water getting into the silo, and even with the motor running is not enough to keep the humidity levels at the correct level. So having this information in a visual way like this would help me take an action and see what is the behavior on each one of the silos that I'm monitoring. Right? And on top of that, obviously, I could also connect additional functions from Azure.
Very interesting. Wellington, I noticed that we're having a pattern that we saw before, which are these dots connecting in certain sections of the graph.
Yeah.
Those are shown when the time series inside has a lack of data for that period of time, which would indicate that the device was probably offline during the time. But we have a basic reconnection logic on our sample, which probably you're using on your project as well. And I can see that it probably automatically reconnected around 9 a.m. and then
yes, 8:48. Yeah.
And it started providing information again.
Yes, great call out. So even though we know that for IoT devices, reconnect and retries are super important, this sample here has the ability to reconnect from both a Wi-Fi fail. So if the Wi-Fi goes down, once the Wi-Fi goes up again, the device will be able to reconnect. And even for scenarios in which it can get to Azure, and we actually even did some tests to go like, if you go to the device, so there is this enable. So if you disable the device, then it won't be able to get the messages anymore. And if you enable it again, it will automatically start sending those data again. Okay, so that was our demo. This is what we wanted to show you today. If you want more resources about the Embedded C SDK, we have plenty for you. So first we have here the GitHub repo where you can find all of our code. It's open source and free. We have some state machine diagrams that you can use to learn and understand a bit more on what is the flow of the Embedded C SDK. We have samples for additional boards like the PIC24. You might want to be taking a look at that. And also we have additional samples for other boards as we saw. There's also a couple of videos that showing a bit more of the code if you're interested, and blog posts. So we hope you enjoyed it. Back to you, Pamela.
Thank you so much, Wellington and Ewerton. This was awesome to see a full end-to-end IoT solution with a dev board all the way, seeing that data go to the cloud, and then being able to visualize the data. So thank you so much for showing. And then for folks who are looking at the links right now, we're going to go ahead and put that in description and then chat. And if you have questions after the event, feel free to add comments in this video or head to our tech community. We have Microsoft Tech Community. All of those links will be in the description for you to reach out to us. So thank you again. Huge shout out to Wellington and Ewerton for doing this and for everyone joining. So we'll speak to you next time. Thank you.
Thank you. Bye.
Bye.